So in this case, we are going to consider a typical exam revision, which is on our statics, working with the beams. This was just a simple beam that we are given. Study the beam shown in figure 2 below and answer the following questions. This is what we had, guys. Let's try to analyze. There is a distributed load here, 80 kilonewton for these 5 meters, 2 plus 3, which is what? 5 meters. So it is actually going to cover 5 meters, this one. It is covering 5 meters. We also have a uniformly distributed load again of 50 kilonewton per meter covering the whole of this section. All of this section. This one. It is covering the whole of the section. Okay. So let's just the question here on 4.11, it was to calculate the magnitude of the reactions. So we have got this reaction and also this reaction. So let's just try to name, just to give points so that at least it can be easier for us guys to answer this. Just gonna call this one A, the reaction. This one I'm gonna call it B. This is an important point. Also, the end of this distributed load, I'm going to call it C. There is a support here. I'm going to call it D. There's a point load here at the end. Let's just call it E. So this is what we can just try to figure out. All right. So let's have our question, guys. Just forgive me here. I'm just gonna do this. I want to use this space here. Just so sorry for that. So this is what we are going to have, guys, according to our question. We are given to calculate the reactions of our support. So let us consider this. This is 4.11. So I'm going to start with D, taking my moments about D so that I can find the value of what? So that I can find the value of B. All right. So taking, that is taking moments about D. So D is this one. All right. So if we are to consider this part of D where we are having our D here, let's figure out how the forces are going to move to that D, especially B, because we want to calculate B. So B, as it is going to go to D, it is going this way. Which way is it? That is the clockwise. This is the way the clock moves, remember. So it is moving, it is maintaining this way, clockwise direction. So that means we are going to refer to the sum of the clockwise moments being equal to the sum of the anti-clockwise moments in that case. So this this B, as it is going to D, it is moving in the clockwise. This is the clockwise. Remember, going this way. Okay, this is clockwise. All right. The opposite, guys, is what? Is our anti-clockwise now. So if it is in the opposite way, that will be your anti-clockwise. So okay, guys, this is your N3. Let us quickly have this. I forgot, guys, it's N4. Now going back like I'm in N3 now. So this is it, guys. Our clockwise. Okay, which other one that we have, which is going to maintain the clockwise? Back to what? Back to D. So remember, this is a distributed D. There's a distributed load. So on the if we check here on the left side of D, everything that we have in terms of these distributed loads on the left side there. Remember, it is going to change and be a point like this, but the direction it will go like this. It will go in the what? Anti-clockwise. So all these distributed loads that we have, this one and this one on the left side, they are going to be going in the what? In the anti-clockwise. So let's not talk about this. Let's figure out what is on the right side. On the right side, do we have anything that is going in the clockwise? Yes. The 50 kilonewton is moving this way, guys, back to D. It is moving in the what? In the clockwise. It's a clockwise. Also, the 50 kilonewton per meter, this one here, it is distributed throughout, remember. So we are going to take the piece of the distributed load here that is remaining here, this one. We are going to take the piece that is remaining for these meters that is remaining for the 3 meters that is remaining, the 50 kilonewton per meter that is remaining here. So you can multiply. If you want, you can just combine this. That will be what? That will be 50 times what? 50 times 3 for these 3 meters. So 50 by 3 is going to be what? 150. So it will be like this now. It will be a point load this time. It will be like just what we have there, the 150. So it will be the same way. So it will be a point load of 150 kilonewton. Separated now, remember the 3 meters divide by 2. So it will be 1,5 here, and we'll be having 1,5 meters there. That is the case. This is what we have on the right side of what? Of D. Because it's distributed throughout the beam. So you have to consider it also on the right side. On the left side, it is moving in the what? Or from the left side. From the left side, it is going in the what? It is going in anti-clockwise. Just like what you did here, you're going to also do the same thing for this remainder. There, I just want you to know the basics, guys, so that it's not gonna affect our question. Here, the remainder of the 50 kilonewton here is going to apply you're going to apply the same thing. Which is on the, remember, you're considering everything that is on the left side of what? On the left side of D. About D, we are talking about D. So on the left side. So on the left side, you can combine because there is also an 80 kilonewton there. Or you work with it separately as it is on the left side as it is. The 50 kilonewton per meter, this one, how many meters does it affect on the left side? That is 4 plus 3, which is 7, plus this one, which is 9. So that'll be 50 times 9. That one. So it'll be 50 times 9. This one. It'll be 50 times what? Times 9, which is 450. So that'll be 450. This one, the 50 times 9, it'll give us the 450, which is in between. Remember, we are taking this one, the whole of this 9 meters. So it'll be simply 9 divided by 2, which is 4,5. 4,5, it's actually, you see, it is covering because 4 meters it's here. So 4,5, it will be going also this side. So it will be somewhere there, somewhere like this. So it will be entering this side. So it will be 400 and what? 450 kilonewton this side. Okay, sorry for that. All right, this one is because I wrote something there, so it's gonna affect. All right, no problem. I wanted to say it was what? 450. Okay, sorry for that, guys. 450 kilonewton. Just ignore that part. So this is the case of what? The 50 kilonewton per meter for these 9 meters. So it will be separated back to what? Back to D. We are focused going back to D. So remember, it was 9 meters, the whole of this. So 9 divided by 2, it will be what? 4,5. So it will be 4,5 back to what? Back to D. So knowing this is just something that you can use, guys. It's fine, but you can even answer without, by looking into the diagram, guys. All right? So it is going in the what? Anti-clockwise. We figured this one for the clockwise, then we figured this one on the other side. The same thing about this 80 kilonewton here. 80 kilonewton is covering how many meters? It is covering 5 meters. So that's 80 times what? 80 times 5. So 80 times 5 is going to be 400. So this one, it will be like this here. It will be 400. It is covering 5 meters, remember? So we multiplied 80 times 5. We got 400 kilonewton. Covering how many meters? It was covering 5 meters. So divide by 2. 5 divided by 2, it will be 2,5. So it will have the 2,5 here. It will have the 2,5 meters here. 5 divided by 2. So back to the point D, you have to add 2,5 plus this 4,5. Guys, if you know this, it's of an advantage when calculating these reactions. Knowing this. This is it's separated. Yes, you can combine the 80 because if you check this section here from A to C, they are using they are actually distributed. Both are distributed here. So you can separate it and have it as a single point. It's still one and the same, but guys, that one will be too much. Okay, I'm just gonna use this one. All right, so this is it. Working with this part, we said the clockwise moment, the sum will be equal to the anti-clockwise. So let's figure out, we said the ones for the clockwise, it's B going to what? To D. So that's B times the distance to D. This distance B to D, that's what? 7. 3 plus 4, that's 7. All right. Do we have anything in the clockwise? Remember, on this side, we talked about these ones which are on the clockwise. They are moving to D like this. It's clockwise. So that is the 150 times what? Times 1,5, the distance between the force and what? And D. So that's 1,5. So if you do not have this 150, you are going to write this one as what? You are going to write it as, remember it is 50 kilonewton. So you write it as 50 times the distance that it is covering on the right side of what? Of D, times the distance that it takes from where it is on the midpoint to what? To D, which is 1,5. You were simply going to take it this way. Let's say you did not calculate separately the way that we did. You're still going to have the same thing, all right? So that's 150 times what? 150 times 1,5. If you have 150, guys, if you have this one, just multiply force times distance. Already, it's what? It's a point load that you have there. It's a force. So just force times what? Force times distance. So that's 150 times what? The distance back to D, which is 1,5. All right. Still on the clockwise, we have this one, the 50 kilonewton at the end. As it is moving back to D, it is going in the clockwise. So that's 50 times what? 50 times 3. So that's 50 times 3. The distance back to D is 3 meters. So that's it. Is equal to all anti-clockwise. Sum of them, the ones that are in the anti-clockwise, you add them, sum of it. So the anti-clockwise, this is the left. These are the ones on the left side. As they go to D, remember this, they are going in the anti-clockwise. So that's 450 times what? The distance back to D. What is the distance? 450 back to D. It's a distance of what? 4,5. So that's 450 times 4,5. 450 times 4,5. All right. We still have another one again, which is going in the anti-clockwise. The 400, this one from 80 times what? From 80 times 5. From that 80 times 5. So it's 400 times the distance back to D. What is the distance back to D? This one. This is the distance. 4,5 plus what? Plus 2,5. 4,5 plus 2,5. So the distance was gonna be what? All right, this is guys, we need this one. All right, this will be 80 times this 5. All right, where am I getting this one will be 4 here. All right, so the 2,5 is it's here, guys. Okay, yes, because I'm now having a lot of things. Sorry for that. The 2,5 is part of the I was taking it to this one. No, 2,5 is here, guys. Here, the 2,5 is going to the end here like this. So it's 2,5, 2,5 like this. So meaning to say, we cannot take the 4,5 because it's also covered here. The 4,5 is there. So what are we going to do? We take this 2,5 and we start here from this one to here. Remember, from here to here, it's what? It's this one, 4 meters. So it will be 4 plus 2,5. Take note, guys. 2,5, it's half of what? From this 80, this one. Half of it, 2,5 this side, 2,5 this side. So the half of it, this one, the half of it, the 2,5, you add the 4 meters. You cannot take the 4,5 because 4,5 is there, it's in within this one. 4,5, look, it is covering, it is entering the 2,5. So if you use it, you must make adjustment to remove this one. You must subtract this distance between here, this one, this one. So guys, it will be a lot. So to avoid that, just take this 4 meters and what? And the 2,5 from the midpoint of the distributed, the one that we now have as a what? As a point load to its end point is 2,5. All right. I hope we are together there. So that's 2,5 plus 4, which is what? Which is 6,5. So that's force times distance. So the distance there was going to be 6,5. All right. So remember, it's what? 400. So that's plus 400 times 6,5. So if you did not use the 400, use 8, it was going to be 80 times 5 times 6,5. So it's one and the same. All right, so this is it, guys. This is your N3, guys. You can use any part that you understand. Here, I cannot say use this way. No, use the way that you understand. So 7 times B, that's 7B. Combine these two. It was going to give us 375, which is equal to everything on the right-hand side, which was going to give us 4,625. So if we take the 375 to the other side, it is going to be negative. So that's negative 375, meaning to say 7B is equal to the difference of these two, 4,250 divided by 7 both sides, so that we determine the exact value of what? Of B. In that case, our B was going to be 607,143 kilonewton. Just like that. So we have our B in that case. We have our B. Just like that. Just like that, guys. Just like that. It's not that much, guys. It's not that much. Do not worry, guys. It's not that much. These things are not that much here. Do not even worry, guys. These things are not that much. So we have our B there. 607.143 kilonewton. This one we could have just calculated even by just looking into the question by sight. You have the question like that. You look into it. This is just for the sake of revision so that all of us, we understand. Anyways, let's see. Now we need, if we are to consider about what? About B, taking moments about B. So this one is no longer valid. We're gonna consider about B this time here, about B. So B is our reference. B, this B here, this B. So if you consider the B that we have there, we must be careful, all right? Taking moments about D, about, we said what? B. Taking moments about B. You must be careful this time. All right, let's see. Right, so taking moments about what? About B, we are going to have this. As we consider D is our support. So D going back to D, it is moving this way. All right. Which way is that one? Anti-clockwise. So as D is moving back to E, this one, it is going in the what? In the anti-clockwise. These ones, they are going to change their directions, guys. Remember, There it has also changed. This one, we're no longer considering this. We are considering D back to what? To B. That is anti-clockwise, this one. All right. So we have got anti-clockwise. So meaning to say we are going to work with sum of the anti-clockwise moments being equal to the sum of the clockwise moments. Let's figure out the anti-clockwise, guys. The anti-clockwise going back to B. Anything going back to B. So if we check this 150, we are no longer going to refer it as 150 because the distributed load of the 50 kilonewton per meter, this one, guys, look where it is, because we are considering it on the right side of B. So you can take it as a combined part this time. It's no longer like this. We cannot take it this way. So this is gonna change actually here. Sorry for that. Let's just try to figure out. So you see moments, guys. But in exam, if you understand these basics, you're not gonna like have a lot of things, guys. Like no problem. But let's figure out these questions. They take a lot of time. But you guys, you want us to work them out. Do this, no problem. We are doing it. Let's do it, guys. So this is it. Sorry for this, guys. Very sorry. I wanted you to see some things properly here that is different now. Even the 80 kilonewton. In fact, guys, let us just remove this. This has changed. This has changed here. All right. Don't mind that part of our. Yeah, we are now considering like this. This is how our question is now considered as from our presentation. If we have this presentation, guys, I want us to see something properly. If we go back to our normal presentation and start again on our diagram, because of these two distributed loads that we have, I want you to see. Yes, you can work with that as it was before. So we said D is going in the anti-clockwise. Okay, this is your D. In the what? Anti-clockwise. Let's figure out anything that is going to go in the anti-clockwise. If you consider this side, which is the right side here, if you consider everything on the right side, all these forces, they are going to be going this way, which is clockwise. Meaning to say, even these distributed loads, as we are going to change them, they'll be point loads. They'll be going to the right. This one also is going to the right, guys. So we're going to recalculate just like what we had previously, to say the 50 kilonewton that is here, this one that is remaining, this one. Okay, let me use this one to say there's a 50 kilonewton here on the right side. We calculate for that 50 kilonewton, guys. There is a 50 kilonewton which is on the left side. So, guys, you see there will be a lot of things. So that is why I say when dealing with these questions, try also as an individual just to know some basic calculation that you can even do them by what? By head, by just looking into the question, okay, here I'm going to simply do it this way. So here, this is what I'm going to do on this side. You understand me? If not, therefore use the previous method that I just explained of splitting our diagram into point loads. All right, so here, guys, we're not going to waste much time. Let's take it this way. Like I said, all right, where did I write on top? No, top like that. No problem. So the anti-clockwise, we are going to have this one, the D, and everything that is on the left side of what? On the left side of B. Everything on the left side of B will be moving this way. This is anti-clockwise. They will be moving this way, just like here, anti-clockwise like this. It will be maintaining anti-clockwise. Everything which is on the right side, all these on the right side, they will be what? For the clockwise. Okay, sorry for that. These ones, they will be for the clockwise. Everything, this one, they will be for the clockwise, meaning to say even the distributed loads, they will be for the what? Clockwise. All right, so if it is like that, guys, it's gonna be easier for us to answer our question because we are going to take it this way. Anti-clockwise, starting with the D. So D back to B, what is the distance here of D back to B? Here, it's 7, what? It's 7 meters. So that's D times 7. So it's going to be D times 7 plus, because we still have the part of the anti-clockwise, this side here. We remember we said this is where we have our anti-clockwise. So let's start with the 50 kilonewton per meter. So it is covering how many meters? It is covering 2 meters. So it is going to be 50. Remember, this is kilonewton per meter. So you must multiply by the distance, which is 2 meters on the what? On the left side, it is covering 2 meters. But if you were to distribute it, like if you were to now separate, have it as a point load, how are you going to have it? It was going to remain with what? 1 meter here. You divide 2 divided by 1. It was going to be what? 1 meter. So you multiply by the distance 1 meter. So 50 times 1, 50 times 2 is to obtain the force. Then times 1, this is the distance back to what? To this point B, about B. This is the one that we are seeing there. All right. So you do the same thing for the 80. You can combine because those two, they are covering the same distance. So you can even add them. 80 plus this one, you can add, then just multiply. Or you can just work them separately. For the 80 kilonewton, it is having the same properties, guys. From the left side of B, it is covering what? 2 meters. So it's going to be 80 times 2. That will be 80 times 2 times the distance back to B. So the distance back to B is what? 1 meter. It's going to divide by 2. So it will be what? 1 meter. So this one is the distance back to what? Back to B. Back to this one. Back to the point B. All right? Is equal to, let's figure out the clockwise. All right, so let's take the part of, okay, we need this value of B. Okay, not it. So let's figure out the clockwise. So on the clockwise, we say these are the ones that are on the right side of B. So let's just start with this one, which is clear. It's 50 back to B. What is the distance back to B? 3 plus 4, 7 plus 3, which is what? Which is 10. Okay, so that is 10 there. Oh, so that is 50 times what? 50 times 10. So I started with the one at the end there. Do not worry. 50 times what? 50 times 10. Okay. Force times distance. We move on to the 50 kilonewton because it is distributed this side also, guys. The left side of this B, there is a distributed load of what? 50 kilonewton. Covering how many meters? For the same number of meters here, it is covering how many meters? 3 plus 4 plus 3, covering 10 meters. So it is going to be 50 times what? 50 times 10. So it's going to be 50 kilonewton times 10. This is the kilonewton per meter, remember. Just like here, this is the kilonewton per meter times 10, the distance to have a force. But how many meters do we have between that force and the on the middle point back to what? Back to B. It will be 10 divided by 2. Remember, the whole of this distance is what? 10. So 10 divided by 2 is what? Is 5. So that will be 5 meters there. All right. So the 5 meters, that is the distance back to what? Back to B. We still have another one in the what? In the in this part of the anti-clockwise. In this part of the clockwise, I mean. Which part are we having in our part of the clockwise? Okay. If we are to consider the part of the clockwise, remember we said these are the ones that we have the 50. We also have the 80. It is on the 80 here. It is on the right side of B. But it is a section of it. It's a piece of it, not all of it, because there was another section which was on the left side of B. There we are concentrating with the section where on the right side of B, this 80 kilonewton, how many meters does it cover? It is covering what? 3 meters. So that's 80 times 3 to have the force. To have the force, it's just to have the force only here. 80 kilonewton per meter times 3, then times the distance back to B, definitely to be 3 divided by 2, because it's that is the only part that we have. Okay, let us just divide properly, guys. 1 comma here, 3 divided by 2 is 1,5, so it's like this. It will be somewhere here like this, covering what? 1,5 this side, covering 1,5 this side. So what we need is this one back to B. It will be what? 1,5. So that's times 1,5. The distance back to what? The distance back to B, just like that. So it's gonna be a lot, isn't it? Just need to work with more questions of this nature. So that is what you do when it is like this, guys. B, there were so many things to consider on B. What is on the right side of B in terms of these distributed loads? They are also on the left side. Same distributed loads. So you work with the distances back to B, divide. Yeah, you're going to have those. So those are like point loads. So guys, it was gonna be a lot of diagram, a lot of point loads. So that is why I say you have a view or in mind. You've been doing this, guys, since N2. Just put it in mind, like what exactly are you dealing with? Anyways, that was gonna be 7D here. Combine these two together. It was going to give us 260 is equal to, you combine everything on the right hand side, is going to give us 3,360. So 7D is equal to, if we subtract 260 both sides, it is going to give us 3,100. So to find the value of D, simply divide by what? By 7 both sides. So dividing by 7 here, that was going to give us 442,857 kilonewton. That's it. That's it, guys. So after that, you can even test your answers. That is it. Just like that. All right. So it was a lot, not that much. It is just for you to understand, but otherwise, guys, it's not that much. Yes, just direct question if you understand this. 4.12, calculate the bending moments at the principal points. 5 marks for that. So for the principal points, we have got the point of inflection, which is where we've got the 0 points, the starting points, the A and the point E. All right, so let me use this side. I can also as well erase at the end. Remember, this is where we had our A, this is our B, our C, our D, and our E. So these are the ones that we are going to use. At A, we calculated this one. Sorry, A is just a point. The way that I'm presenting now is like, it's like we have a support there. This one is just, guys, so that it does not confuse us here. So we calculated B, actually. Calculated B, it was 607,143 kilonewton. We calculated this one. Okay. We also calculated D. It was 442,857 kilonewton. All right. To like this. We calculated this D. So working with the bending moments, guys, I talked about this. We're gonna consider at point A, we do not have anything on the left side of A. So meaning to say the bending moments at A is just going to be 0 there. Force times distance. We do not have any distance covered there. All right. So that is it. Remember, this is 4.12. Remember for the bending moments. Then the bending moments, the bending moment for B. For B, if you consider, yes, it's up to you guys. You can consider from the right or from the left, but it was easier working from the left side because we look, guys, we just have few things done here on the right side. Yes, you can even consider the right side, but what is it that you're going to have? Remember, bending moment, guys, force times what? Force times distance. So in this case, considering to the left, all right, to the left. Remember, we are focusing with the B here at B. So to the left of B, there is a distributed load of 80 kilonewton, this one, which is covering what? 2 meters to the left of B here. It is covering 2 meters. So it is going to be just like what we had, guys, previously. So you're going to have 80 times what? Times 2, then times the, okay, this one is actually a negative. Remember, it will give us a negative when it is a point load. It will change to be a point load like this. So it will carry a negative. So that will be negative 80 times 2, the distance where it is distributed for 2 meters. All right. Then the distance back to B, because we have to consider the distance back to B. So it will cover 1 meter back to B. So this 1 meter is the distance back to B. All right. So it's a negative. Also, there is a 50 kilonewton there on the left side of B here. There's a 50 kilonewton. So you do the same thing, guys. It will carry a negative. So it will be negative 50 times 2 times the distance back to B to cover 1 meter there back to B. So that is the case of your question, guys. All right. Combine everything here. That was going to give us a negative. All right. So that is negative 260 kilonewton meter. Just like that. So that is the bending moment that you are going to have. So guys, you can also consider from the right side, you do the same thing, meaning to say this 80, it is covered for what? For 3 meters. So it will be 80 times 3 times 1,5, the distance back to B. You do the same thing for the 50. Then you also take this one, everything, knowing that they are having a negative and there's a support there, which is having a positive. So you have to add it, force times distance back to what? Back to D. So guys, it's up to you to do that. All right, so let's move on to another one. Bending moment, we also have the point C. So using the point C, okay, this is it. Let me just remove this one, no problem. Let me just do this. So for C, we are considering C this time. This is where we have our C here. So if you are to consider C, it is up to you again. Are you going to work from the left side or from the right? So if you consider C, there's a lot on the left than on the right. There is 80, there's the 50, there's also this support. So you can just work it from the what? From the right, because on the right, we only have one distributed. Yeah, there are 2 distributed load that you have to compare again. I'm not saying it's wrong to work from there, but as for me, guys, I'm going to compare from what? From the right side or to the right side. So to the right, taking this one, it is going to be, let's see, there's a positive there to the right. There's a positive. Remember, there's a support on the right side of C. We are focusing on the right side of what? On the right side of C. There is a support there. So it's force times distance back to what? Back to C. So that's a positive. This one, 442,852 times the distance back to what? Back to C, which is 4 meters. So that's 4 meters. Okay. That is D, which is positive. Then we consider the negative now, which are the ones which will be the point loads. This one a negative, and this part of the distributed load, it will end up like this, carrying what? A negative. So let's start with the 50, guys, which is direct, this one. So it's 50 times the distance back to C, So the distance back to C, that's 3 plus 4, which is 7. So that's minus, it's carrying a negative. It's a point load. So that's minus 50 times 7. Then we also have that part of the distributed load. So like I said, guys, it will actually definitely be a point load. So it will carry a negative. So it will be like this. In between, it is covering how many meters? 7 meters to the right side. We are focusing on the right side of what? C. The right side of C. It is covering 7 meters. So it's 50 times what? It's 50 times 7. So that is what we have there. But that 50 times 7 is going to be taken in between how many meters? 7, the distance 7 divided by 2, it's what? 3,5. So it will be 3,5 back to C, 3,5 to what? To E. So as we need the distance back to E, which is what? 3,5. So that's 50 times 7 times 3,5, or we can just multiply 50 times 7, which is what? 350. So you can just write 350, or you can just write 50 times 7 times the 3,5 is the distance now that you take that when it is a point load back to what? Back to D. Remember, it will be separated into 2 equal parts. So that is it, guys. Just like that. You have the bending moment at what? At C. Just like that. So that was going to give us that was going to be a positive, this one. So it's positive 196,428 kilonewton meter. So that is it. Just like that. All right, then we move on to the last part. Okay, not the last part actually, but to this one for D. So if we consider for D, this part here of D, guys, this is where we have our D this time. So considering where D is here, this is where our D. It'll be easier, guys, to work from the right. Look at the left, guys, there's a lot. So it'll be easier for you to take your moments like working from what? The right side. All right. So the right side, we just have a few things there. So for the bending moment there for D, it is going to be what? What is on the right side? Algebraic sum of these moments on the right side. So we do not have anything with a positive. Remember, D is not included. That is where we are referring to. So we are going to talk about this 50. It's a negative. Back to D, it is covering what? 3 meters. So that's a negative there. So that's negative 50 times 3. There is a distributed load here, so it's going to be negative D here, the right side of D here. There's a distributed load, the 50 kilonewton per meter, this one, covering how many meters? Covering 3 meters. So that's 50 times what? 50 times 3, which is 150 kilonewton. But it will be separated now in between, just like the previous case. 3 divided by 2, 1,5 here, another one, 1,5 there. So that will be 150 times what? 1,5. So you're going to subtract that one. Remember, it's a negative. So that's 150 times 1,5. So the 1,5 there is the distance that we are taking back to what? Back to D. So that was going to give us a negative 375 kilonewton meter. So it was going to be a negative. Then the last one at the end point at E, and we do not have anything on the right side. So we do not have a distance to be taken from the right side. So meaning to say that will be a 0, that one. Do not waste your time to calculate even if we can calculate it from the left side, guys, do not waste your time there. Remember this one we took to the right. Okay, it was to the right. Okay, then the bending moment now at what that's for E. So for E, we said it's gonna be what 0 kilonewton meter. That's it. So these are the ones that we needed in this simplification, guys. We needed this. We actually needed these values. All right. So after that, the question on 4.13, it was now to draw the bending moment diagram. That was 3 marks for you to have the bending moment diagram. So if you are to consider, I said when you are to have your bending moment diagram, here we've got a distributed load. It's distributed throughout, it's distributed, guys. So meaning to say, we are going to be representing in form of what? In form of a curve. In form of a curve. If you're going down, but it'll be in form of a curve when it is distributed, when you're representing what? The bending moment. Also, on the bending moment diagram, we calculated those bending moments, but we need where it is going to be maximum. Where do we have the maximum bending moment? So that part, it is easier to see if there is a shear force diagram, and of which in this case, we do not have a shear force diagram. But based on the understanding of our shear force diagram, we can see that it was going to be like this. I just want you to see the basic view of how it was going to be like. It was going to start at 0, definitely. Then we do not have any reaction here. The reaction is at B. So there is a distributed, another distributed. So they will be distributed, guys, distributed. So they will be going in the what? In the negative, like that. Distributed, I do not know, to a certain value there, which is the sum of those two. Remember, it was minus 80 times 2, which was what? Minus 160. And the 50 times 2, which is 100, minus 100. So it will be at minus 260. I'm talking about the shear force diagram. It will be minus 260 kilonewton there. Then there's a support at B. This one, there's a support, this one at B. Remember your support B, it was 607,143. You add it to the support, you add to this one. Remember the support, guys, it goes up. So if we add this value, it was going to be like this, going up. I just want you to see the basic view of how it was going to be like. You just figure out in your head, like, okay, I have got a value there, and this value, if you add to minus 260, this one, 607, we combine with minus 260. It was going to be 347,143, something like that, kilonewton. Distributed again, this one and this one combined together. You add them, you combine them together, you subtract. So definitely this one, guys, was going to cross like this, go to the negative. Where it crosses there, where it crosses here, where we have this distributed and it is crossing like that. That is where we have our maximum bending moment. It is going to occur at that point. So let's say that point is called X. That is where we have our maximum bending moment. All right. So it was gonna be something else, guys. You have to calculate that. So remember, I talked about the formula that if you are given, let's say you've got a boss, if you're dealing with shear force, even on the bending moment, you see that this point where it was going to happen on my bending moment, because I'm having my bending moment, maybe it's like this. Then there's another section like that. You know, okay, when the shear force was being drawn, it was like this, guys. It went up. Then when it went up, the part when it is going down there, that is where we are having what? The maximum bending moment, the maximum. So even there, you can even calculate this distance. You can even specify the distance. If you have accurately drawn value, like a diagram is actually drawn to scale. But in our case, it is not drawn to scale. So what are we going to do? Remember what I said? I talked about this section from the introduction. I talked about this section here to say, let's say I've got this section here. You can calculate the maximum bending moment if you know the distance that you take here as y here between these 2 points. Remember, I talked about this. So how do you find this y? You just calculate the forces at this point where you have the maximum bending moment at this point. They will be equal to 0. So we can simply calculate because already there's a force there that we are given 347, 143 minus force times distance. Remember, there's this distributed load here. The distributed load FD, remember I talked about this on the introduction. So you take the distributed load, but take note in our case, our distributed load, it is two things, the 80 and the what? The 50. The 80 and the 50. So you add them together. They are one part. So 80 plus 50, it's what? 130. 80 plus 50, the distributed load. You combine them. So it will be 130. So that will be 130 times what? Times y is equal to 0. So you find the value of y, which is the distance that we have here, the distance there. So that is it, guys. 3, 4, 7. In terms of calculations, but if you have an accurate diagram, there's no need for you to calculate this. If your diagram is up to scale, you simply use the scale. But guys, our boards here, we cannot have a proper scale. So we just need to do by calculation. So it was going to be 2,67, something like that, meters. This is the distance here. So with the distance y, I said you can have your maximum bending moment. Actually, I talked about this formula that you can use if you watched that part of our introduction, that for that maximum, I want you to be clear on the formula because here we are going to have an adjustment. So this is your y, guys. This one. This is your y, which is 2,67. So if this part was not there, you were going to calculate your maximum bending moment using the formula that I said you can use. This force here, let's say this is your point A. So you call FA times y minus the distributed load times y squared over 2. So that is our FA was going to be 347,143 times y there. This y, the one that we calculated, 2,67 minus the distributed load. Remember, I talked about the distributed load that we combined it together. 80 plus 50, it was now what? 130 kilonewton per meter. So that's 130 times y, the distance, y squared, 2,67 squared over what? Over 2. So that was the formula that I gave you. And this formula was supposed to give you the maximum bending moment from what I explained on the introduction. But if you also consider what I said on the introduction, I said adjustments can be made on that formula, like what we have here, because it was supposed to be maximum. But look, there is another part that we covered here. There's another part that we covered, which is in the negative region, right? In terms of the, sorry, here, where are those ones? The negative, this one, the negative 260 kilonewton per meter. It's already covered. It will be in the negative region like that. So we have to add that one to it to reach the maximum. We must add the one that we got because already there's a negative before. There will be a bending moment there, which will be at negative 260 kilonewton meter. So you must combine the two now. So therefore, our maximum bending moment was going to be 463.493 minus, because it is carrying a negative, the 260 there. So it was going to be, you're going to subtract. So it will be at 203.493 kilonewton meter. So if your diagram is up to scale, guys. You just need to find the value of y direct, then you can calculate your bending moment with the formula. But here we had to calculate the y first, then the bending moment later on. So we just need to see what's gonna happen, guys. My board just erased everything. No problem. So here, guys, let's just do this because you see these softwares, guys, I always say they tend to just misbehave. But we saw that our maximum bending moment was gonna be what? Was gonna be at 203.493. There are actually so many ways, guys. If you've got an accurate diagram, so many ways. So if you got another way, guys, you can explain. Just put a comment section. On the comment section, put a comment so that I can or even you have my contact, guys. You can even check my contact so that we can communicate. If you have another method on WhatsApp, let's communicate. So it means as we had, definitely, guys, we saw the bending moment there that we had, the ones that we calculated. The one at B, it was negative 260. We had that the bending moment at B, remember, it was negative 260 kilonewton meter. For C, it was 196,426,428 because my board, guys, just removed everything. Then at D, it was negative 375. At A, it was 0, and at E, it was what? 0. So you can see 203 is the biggest one, which can be found actually because it's going to start at 0. Then it go to the negative. It's in the negative region. So when it is moving from the negative to this point C, that is where in between we have that maximum. So it was going to be like this. All right, let us quickly have our diagram before this board starts to complain. It actually, maybe I explained a lot of things that are just to explain, guys, you know. These explanations, sometimes you might think someone have understood, while someone haven't. Someone have understood more and saying the explanation is too much, you must remove. Someone will be saying your explanation is you need to add more. So guys, it will be difficult to understand you guys, but we just try. We are teachers. We just try to understand you as much as we can. So this is it, guys. This is it. For the bending moment, we're gonna start this as our 0 point, which is at 0 kilonewton, 0 kilonewton meter. All right. So it went to the negative at B, negative 260. All right. It went to the negative. So it was just gonna be negative. Just gonna be negative 260. So maybe according to your scale, guys, remember, as for me, guys, my scale is my side. So that you are supposed to just have a simpler scale. Let's say this is where we have negative 260 kilonewton meter. Remember, it's a distributed load. And I said for a distributed load, if you are working with the bending moment diagram, it's supposed to be a curve. All right. So this one will be a curve, but in the negative. So it's just going to be a curve. Just going to put it like a curve. Okay. Here. Okay. It's only that that board was removed. So I can't even have those presentations that I explained before. But I hope you understand. So it'll be a curve like that. So when it is moving from B, now when it is moving from this now to this C, it is 196. Definitely it must pass the maximum because it is 200. So it has to reach 200, then to 196. But it's in the form of a curve, guys. It's distributed throughout. So it is, as it is going up there, it will be distributed, guys. It will be in form of a curve. Remember, it is distributed. So it will be in form of a curve. It goes to the maximum. We do not know exactly where that maximum value is going to be. Sorry guys, here I just need to have something like this. Then it has to go back. All right. Just to go back to the point B. It's now C. 196. 190. 196. That is 196,428. All right. That is what we have. Then from this one, it goes to D, which is in the negative. So D, as it we have there, is in the negative. So it was going to be a curve again, guys. On this, a curve to a curve to the negative, just a form of a curve, but it's going to reach the negative, this one. It's going to be to the negative. Negative 376. Negative 376 is below this one. So it's going to go somewhere there. So let's say this is where we have got negative 375 kilonewton meter. Then finally to E. Remember, it's distributed. So as it goes, as it's going to go back to the point D, to the point E, which is at 0 on the ground, it's still a curve. So it's going to be in the form of a curve like that. It's now at what? At 0. So that's 0 kilonewton meter, like that. So this is it, guys. You can have that presentation. So just try to work out as many questions as you can. You can actually have a simpler presentation, guys. This is just for the explanation so that all of us might understand. Just try to do more questions. You see that it's just direct like this.